Okay, so we've got this string here which is suspended from the ceiling at point B. Okay, and at the other end of the string is this mass of 3 kilograms. And the modulus of elasticity of the string is 294 newtons. The natural length is 2 meters. So in A, it says the particle P is suspended in equilibrium. Calculate the extension of the string, AB. So it's no longer going to be 2 meters, isn't it? Because you've got this mass at the end, which is pulling it down, so stretching that string. Okay, but what we can say, okay, is that it's in equilibrium. Yeah, because it says clearly there in the question. Okay, so when we apply Newton's second law, okay, because it's in equilibrium, then we can say that the forces balance. Yeah, so in other words, the tension in the string has got to equal the weight of the particle. Okay, so the weight will be 3g. So now we know the tension, we can then apply Hooke's law. Okay, so Hooke's law says that the tension is equal to the modulus of elasticity of the string times the extension divided by the natural length. Okay, so if we sub in the tension there, which is 3g, the lambda is 294. Okay, well, I don't know what the extension is, but I know the natural length is 2. So I can just play around with this to work out what x is. So 3g, well, g of course is 9.8. 3 times 9.8. Take the 2 over and multiply by 2. And then you're going to divide by that 294, and that will give you the x. So the extension will be 0.2 meters. Okay, so all in all, A, if you think about it now, will be 2.2 meters below B, yeah? Because you've got the natural length of the string, just 2 meters, plus this extension, so it'll be 2.2 meters. So that's going to actually help us then with B, because in B, it says the particle P is held at a distance of 1.2 meters, okay, below A. So this is where it is to start with, and then it says released. Determine the speed of P as it passes through this equilibrium position. Now, of course, because we know the equilibrium position is 2.2 meters below the ceiling, B, this obviously then has to be 1 meter, yeah? Because if it's starting at 1.2 meters below B, then of course another meter is what's needed to take us to the equilibrium position of the string. Okay, so we need to find the speed when it passes through here. So it's released here from rest, okay, because it's held, it says, yeah? It's held and then released, so that means here it's at rest. Okay, so what we need to do is look at the energy to start with. So the energy, say, at A here, okay, we call it A here, at the beginning. So that will be, well, if you think about energy, we've got 3 types, yeah? Kinetic energy, potential energy, and elastic potential energy. Well, it's at rest, so the kinetic energy will be 0. Now, potential energy. Now, what I've done is I've set this to be like my 0 potential energy at the equilibrium position. It makes sense to do that. So this is like the ground, if you like. So here, it's like 1 meter above the ground. So we are going to have potential energy there. Let me write the formula to start with, but we know H is going to be 1. Okay, and elastic potential energy. Well, if it's held 1.2 meters below B, and the string is 2 meters in length, then it's obviously going to be slack here, isn't it? Okay, it's going to be wavy like that. So there's not going to be any energy stored in that string. So that's going to be 0 as well. So the energy at A will be the mass then, for the potential energy, the mass, which is 3 times gravity 9.8 times the height then. So the height of it at A is 1 meter above the ground. So you work that out, okay, and you get 29.4 joules. Okay, so the energy then at the equilibrium position, okay, so the energy, say, well, we'll call that C maybe, okay. Well, again, we'll consider both kinetic energy, potential energy, and elastic potential energy. Okay, well, the kinetic energy, obviously, we're going to use that formula, half mv squared, okay, for kinetic energy. Potential energy at C, well, it's going to be 0, isn't it? Because that's like the ground level, so to speak. And then the elastic potential energy, okay, well, we at this position here, obviously it's going to be lambda, okay, x squared over 2l. So that formula, we're going to use that because it's going to have energy stored in that string because the string's stretched. So let's figure out what we know. We know the mass obviously to be 3. We don't know. We're going to work that out, and then we can work the energy out here. So the lambda is going to be 294. Okay. The extension, okay, at there. Well, remember we worked out the extension at the equilibrium position to be 0.2. Okay, so we worked that out in part A. And the natural length then of the string is 2 meters. So when you work all that out, we get 1.5 v squared here. And I worked this out earlier, that came out to be 2.94. Okay, so then the energy is conserved, isn't it? There's no loss of energy. So by conservation of energy, the energy that we have at C, which is this, will equal to the energy that we had at A. Okay, it'll balance out there. And if you take this over, you have 1.5 v squared is 26.46, which means then when you take the 1.5 over and divide, you get 17.64 here. So then v comes out to be 4.2 exactly meters per second.